This is a simplified version of Galileo's formula because the students won't look at the separate x and y components until physics. We want the students to view the top equation as a formula for variable definitions and for learning the new vocab, such as initial height, initial velocity, and gravity. But we also want the students to view the equation as a quadratic and to be able to manipulate it to vertex form. Projectiles are a special type of quadratic, and there are some characteristics of projectiles that will always be true. The value a will always be negative. A sad graph opens down, whether it is thrown upward or downward. The important part of the graph is restricted to the first quadrant. We can still graph the entire projectile equation, but the only part that is relevant is when time is positive, not back to the future, and when h is positive. The g value will either be negative 9.8 meters per second squared or negative 32 feet per second squared, depending on if you're doing English or metric units. Not only can we find the vertex, which is the maximum height, and the roots, which is when the ball is at a height of 0, we can use the aforementioned equation to find acceleration and velocity. These are concepts that will be very important for students who go on to take physics. The formula manipulation that is required to solve these quantities will be important in both chemistry and physics and will also help the students solidify their algebraic equation manipulation skills. Students often become fixated on the quadratic formula because it will work with any quadratic. They want to use it quickly and all the time, even when it doesn't make sense to use it. I made an analogy for how algorithms have played a role in the development and use of the quadratic formula. As all the mathematicians were developing ways to solve quadratics, little roads were built and dead ends were met. When the quadratic formula was developed, the Autobahn was created. For those of you who do not know, the Autobahn is a German expressway with no general speed limit. The Autobahn quadratic formula allows us to go straight and very quickly to the answer. However, for students, the Autobahn can be treacherous, especially if they can't drive through an equation well. Often students make mistakes when using the quadratic formula, and they're squaring, or they forget their negatives, or they forget to put the equation in standard form first. They will use the quadratic formula even when it's easier to factor. They will also use it when you can take the square roots of both sides to solve. That's where the algorithms come into play. Algorithms allow us to create shortcuts and side roads. Why take the interstate if your destination is down the street? Why use quadratic formulas when you can easily factor? This brings me to my algorithmic approach in the classroom. I am very procedure-oriented in my class, so I thought it would be a great activity to have the students write an algorithm for solving a projectile problem. Like I said, students learn the quadratic formula and then try to use it everywhere, even when it doesn't make sense. So let me boot up my example. So this is a sample algorithm that I made, giving a general idea of what I would like the students to do. The algorithm starts with the easiest variables to solve for and moves to the more complicated ones. So my step 1 is to make sure your units are either all English or all metric and convert as needed. Very important first step is to make sure all your units are the same. Step 2, the easiest variable to solve for is h of t. As you can see from up here, h of t is already isolated. So when I know all of the other variables, I can just plug them in, simplify, and there's what h of t is. I also have a reminder in here to put units on. I know that students like to forget those with story problems, so this is all part of the algorithmic procedure. Next one, solving for h naught. They would use a manipulated equation to fill in all the known values and then compute the right side. So this is where we get into that chemistry application of doing manipulations of the equation. So by moving h naught over to the left side and h of t over to the right side, we now have a new equation that's isolated to solve for h naught. And we can do the same thing if we are solving for g. For example, if our gravity is on the moon instead of our normal gravity, we could solve for g using a different manipulated equation. And it isn't until step 5 that we actually start solving for t, which is our roots or our x-intercepts. Now, when our initial velocity is 0, we can just use square roots and a manipulated equation to find out what t is. we don't even have to use the quadratic formula. So steps 1 through 5 is just equation manipulation, simplifying, and solving. All Algebra 1 stuff. It isn't until step 6, where we have an initial velocity that is not 0, and we are solving for t, that we get to take a different route. So when the students are making their algorithm, I would encourage them to maybe do a flow chart or draw a diagram for how they would determine how to use each of these individual steps. So step 7 says factoring. If you can easily factor the quadratic, do so. Now the students might have more in-depth explanations of what easy factoring is. So for example, if it's a special case like a perfect square, maybe they wouldn't factor that because they struggle with those a little bit more. Or a special case such as difference of squares, maybe they would move on to the next step. But the algorithms would be in place so that the students know what works best for them. So really it would be a personalized algorithm of what works best for the students. Next, for step 8, I have completing the square. Now I have in the algorithm here that this method is preferred if you must also find the maximum height or the time it takes to get to the maximum height. And the reason I have this is because when you complete the square, you are essentially putting the equation in vertex form minus a couple of little steps. The little danger zone with this is, notice that our vertex has the variables of h and k. So if the students are working with the manipulated equation and getting to vertex form, it's very important that they realize that this is different than h naught and h of t up above. So it isn't until step 9 that we even have the option of using the quadratic formula, unless of course the students didn't want to factor or complete the square. But step 9, we finally get the opportunity to use the quadratic formula. And I would probably encourage the students to put little warning flags in their algorithm, like watch out for squaring negatives and make sure to simplify the square roots. And step 10 is the calculator. So this would be if they don't need an exact answer and are looking for a decimal estimate, I would allow them to use the calculator. For the next 3 steps, these are the ones that I have laid out for finding the maximum height or the vertex of the equation. So if they didn't have to do any completing the square in the previous steps, they could do step 11, which is the standard form equation using negative b over 2a to find the vertex and its y-coordinate. And number 12 is completing the square again, where the student can just pull out the vertex from those values. And the last resort is the calculator to find the maximum using the max key. So this just gives the students the opportunity to lay out a procedure for solving. I think this would help them figure out where they're going wrong, or when they're making too much work for themselves and trying to plug things into the quadratic formula when they really don't need to. So that would be the type of activity I would want to do in my classroom. So in conclusion, students can use this activity to check their work and the work of their peers using their algorithms, and also help each other develop more specific steps. Students can also create a more exact methodology for problem solving and will learn the benefits of a structured, creative problem solving process. Thank you so much for your time today.